This video will lead through some mole conversion problems with elements and with compounds. Just a reminder, remember a mole is a counting unit in chemistry. So if we would choose any of our elements, let's say aluminum. Well, if we have 1 mole of aluminum, that means, since this is an element, that we would have Avogadro's number of atoms of aluminum. And the mass of that 1 mole of aluminum would be the average atomic mass, and we know that we are reporting those to the 100th place. Well, so we can relate grams to moles using average atomic mass and relate moles and atoms. If it's moles of an element, well then we can go back and forth using Avogadro's number. So those are kind of our problem-solving methods. However, we're not going to memorize this. We're just going to take what we're given, know the relationships that we can use, and work our way to the answer. So I'll just choose a couple of the problems from your unit packet to walk us through, and then I'll share with us the work and the answers for all of these. So what if we just choose an even one? How about number 2? All right, number 2 is asking for the number of atoms in 3.76 times 10 to the negative 5th moles of iron. All right, I'm given moles, but I want atoms. Okay, so I know I will definitely cancel mole in the bottom of my first conversion, and I know moles to atoms of an element, I can use Avogadro's number. And that's the number of atoms in 1 mole. And our sig figs, I'm going to go ahead and say that the mole was obtained through measurement, and so I'm limited to 3 significant figures. Now, Avogadro's number could limit us. It comes from experimentation, could limit us to 4, but we're limited to 3. And the correct answer is 2.26 times 10 to the 19th atoms, and we want to identify what our element is, or our compound. It's iron here. Okay, well, what if, let's choose, how about, number 1. Determine the mass of 2.50 moles of nitrogen. Okay, I'm starting with moles just like I did there. But here, it's not involving atoms. So I don't need Avogadro's number. I need to get out of moles and into grams. That's where I rely on the average atomic mass. 1 mole of nitrogen is 14.01 grams. And so I will be restricted to 3 sig figs, 35.0 grams of nitrogen. Now, I always have some students that just are Avogadro's number crazy, and they want to put Avogadro's number in every single conversion. But we only need Avogadro's number with elements if we're given or we're asked for atoms. Here we're not. So we pull grams, of course, from the average atomic mass value. All right, what if we were asked number 5? Determine the mass of 3.01 times 10 to the 24th atoms. Okay, so I'm probably going to need Avogadro's number of fluorine. All right, I know I want to cancel atoms. Well, where do I go from there? Atoms get me to moles. And I know in 1 mole of an element, there's Avogadro's number of atoms of that element. Okay, got rid of atoms. Now I'm in moles. And I know moles get me to grams using average atomic mass. And every 1 mole is 19 grams. Atoms, that's counted. That will not limit me. This could limit me to 4. This could limit me to 4, so I'm limited to 4. And so what we should have, let me just recalculate to make sure I am reporting and being so careful that we are utilizing our exponential key. And our answer is 94.97. 0.97 grams of fluorine. Okay, now what I encourage you to do, if you're just following along with the video, is try a couple of these yourself. I'm going to show you my answers. Please try a couple of these yourselves, then check with mine. And I need to change this to be 94.97 grams. Oh, I need to check. This should have 4 sig figs. But if you want to pause, check your work with mine. But this should have, again, that should be counted. So this should have 4 sig figs. Go ahead and pause me, because now I'm going to move onward to our next page. All right, so now we're going to take a look at, well, what about compounds? So let's look at probably the compound that we're most familiar with is water. Well, I know I can have, 1 mole of hydrogen, and that's Avogadro's number of atoms and, the average atomic mass. But can I also have 1 mole of a compound? All right. Can we talk about, if we have 1 mole of element, the smallest piece, so the pieces that make up this mole are atoms, right? We have Avogadro's number of atoms that give me a mole of element. So if I have 1 mole of oxygen, it is Avogadro's number of atoms of oxygen. All right. But what if I have 1 mole of compound? For right now, we're just going to talk about covalent compounds. So we're just going to be dealing with compounds that are just made of non-metallic elements. But for just our first use, we're just going to, call them compounds. All right. Well, the smallest piece of a compound is a molecule. Okay? Molecule are 2 or more nonmetals that are sharing electrons, that are chemically bonded. So if I have 1 mole of compound, it's Avogadro's number of molecules of that compound. So if I would have 1 mole of water, it would be Avogadro's number of molecules of water. Okay? Just like if I had a mole of pens, it would be Avogadro's number of pens. Well, I can have 1 mole of staplers, and that would be Avogadro's number of staplers, not pens. So we have to know what we're talking in terms of. Well, if I have 1 mole of compound, what mass would that be? Because I know 1 mole of oxygen is the average atomic mass of oxygen. So how do I find the mass of a mole of compound? Well, that is called formula mass. And sometimes we also call it molar mass, which is kind of silly because molar mass would be the mass of a mole. Well, isn't that what this is? So we sometimes are silly and use molar mass in exchange with formula mass, and we mean the mass of 1 mole of our compound, our formula. How do we find this? Well, we look at our formula, H2O, and we break it down into the elements that make it up. So H2O is made of hydrogen and oxygen. All right. These smaller numbers are called subscripts. They indicate the number of each element, the number of atoms of each element. So in 1 water, I have 2 hydrogens and 1 oxygen. Hydrogen is the average atomic mass of 1.01 gram per mole, and oxygen is 16 gram per mole. When water, I have 2 hydrogens. So actually those 2 hydrogens deliver 2.02 grams per mole of water, where there's just 1 oxygen that delivers 16. So then adding these gives me what's called the formula mass or the molar mass of water. This is the number of grams of H2O that are in 1 mole of H2O. So the official units would be gram per mole. Or I could write it this way, like a conversion factor. Let's do another. What if I would have KClO3? Well, what is the formula mass of that? I have 1 potassium, 1 chlorine, 1 oxygen, or I have oxygen. And if I interpret my formula, 1 potassium, 1 chlorine, but 3 oxygens. Potassium is 39.10 gram per mole, chlorine 35.45 grams per mole, and oxygen is 16 grams per mole. I multiply, I get 39.10 grams for potassium, 35.45 for chlorine, and then 48 for my oxygen. I just want to double check. 39. And I am reporting these to the 100th place as well, respecting significant figures. So the formula mass of KClO3 is 122.55. So 1 mole of KClO3 is 122.55 grams of KClO3. This is a compound. But notice, it's ionic. Ionic are made of metals and non-metals. We know where our elements are. So we can start to learn this terminology. This is an ionic compound. The smallest piece of an ionic compound is a formula unit. So if I have 1 mole of potassium chlorate, it will be Avogadro's number of formula units. All right. Now, sometimes we have what are called polyatomic ions. We will get to know those. So, for example, magnesium hydroxide. This formula is written in this way because hydroxide is what we call a polyatomic ion. What this means is this is a collective group and I have 2 of them. So I have 2 hydroxide groups, which would give me 2 oxygen and 2 hydrogens. But what I can do is just apply the subscript and multiply it by the subscript that's on the inside. So in magnesium hydroxide, I have 1 magnesium, but I would have 2 oxygen and 2 hydrogen. In aluminum carbonate, I would have 2 aluminum, I would have 3 carbon and 9 oxygen because I multiply. I then would get the average atomic mass of the individual elements, multiply, and add those to get the gram per mole, or the formula mass of aluminum carbonate, mass in 1 mole of aluminum carbonate. All right, let's try a couple of the problems dealing with compounds. Okay, so what if, again, let's try, let's do 5, an odd one. All right, number 5 reads, find the mass of 2.8 times 10 to the negative 4th mole of calcium chloride. Okay, it's a compound. Now, I need mass. Can we relate moles and grams? Absolutely. We get our information from the periodic table. Now, since we're kind of new to this, I encourage you over on the side to get the formula mass. So calcium chloride, 1 calcium and chlorine, but I have 2 chlorines. Calcium is 40.08 gram per mole, chlorine 35.45. I do my multiplication, and this will be, 70.90, add them up, and this is how many grams there are in 1 mole of CaCl2. So, moles will go on the bottom, and I just found that 1 mole, that casts a glare, I'm sorry, 1 mole is 110.98 grams. And so, I just do my math, and this would limit me to 5, but that's to 2 sig figs. And my answer is 0.031 grams of calcium chloride. Okay, let's do one more, and then I'll show you my work. Okay, what about number 6? So, how many molecules are in 8.905 grams of C6H12O6? That's glucose, by the way. All right, I need to cancel grams. Where do we go from grams? Moles. It is a formula made of carbon, hydrogen, and oxygen. I have 6, 12, and 6. This is 12.01 gram per mole. This is 1.01 gram per mole. This is 16. So, doing our multiplication and then addition, we will get 180.18 gram per mole. So there's 180.18 grams in 1 mole of C6H12O6. Okay, do I have to write the identity of the compound? Yes. A little bit of graphite or spent ink is fine. All right, now I'm in moles. I was asking for molecules. That's because this is a compound. It's covalent. It's made of all nonmetals. And I know the smallest piece of a covalent compound is a molecule. So I can use Avogadro's number. All right, of C6H12O6. Okay, and then doing that math, and this has 4 sig figs, this and this have the potential to limit me, and I get 2.976 times 10 to the 22nd molecules of C6H12O6. All right, so If you would like to examine, please try some of the others. Don't just look at my work, please. I'm going to focus it so it'll get fuzzy for a second. Please don't just look at my work. Please try these and then compare your work to mine. Okay, best of luck.